This animated diagram illustrates a classical generalized method of moments, or GMM, estimating equation in perfect balance. In classical theory, this balance relies on perfectly specifying moments prior to observing data. Modern workflows operate differently. Researchers compress massive dictionaries of candidate instruments and inject these data-derived components directly back into the core equation. This sequence introduces a severe structural error. The researcher evaluates this newly assembled model on the exact same dataset that was used to discover its components in the first place. By recycling the data, the process forces the selected mathematical component to act as if it were fixed in advance. The inherent uncertainty of the algorithmic search process is completely masked from the final calculation. This double-dipping creates extreme relevance inflation and severe adaptive bias. Because the model ignores the selection step, the resulting standard error calculations become meaningless. Treating data-derived features as exogenous inputs invalidates the standard root n asymptotic limit theory that practitioners rely on to prove their findings. This chart visualizes a controlled simulation of an instrumental variables model. We start with 80 candidate excluded instruments and a true target parameter of 1.0. Looking at the Oracle IV row, we see a perfect 1.0 parameter recovery. But when we apply a same-sample adaptive approach to select and estimate on identical observations, a significant upward bias appears, locking in at 1.0980. The root of this failure is algebraic, detailed here in Proposition 13. We calculate the expected value of the adaptive noise, and the term does not converge to 0. Instead, it converges to d rho over n. Because the same data is used twice, the dynamically selected direction vector aligns with the exact sample noise in the test statistic. The algorithm optimizes for noise, treating it as signal. This mechanical alignment artificially inflates the relevance of weak instruments. It tricks the model into a state of mathematical overconfidence. Without severing the selection channel from the evaluation channel, any same-sample adaptive search guarantees false precision. The structural solution to this problem is cross-fitted adaptive estimation, or CFAE. This framework shifts split-sample logic out of the informal pre-processing stage and embeds it directly into the estimating equation itself. This diagram shows the foundational step, partitioning the master dataset into independent folds, creating a training block and validation block. The training fold has an exclusive mandate to run the adaptive search and learn the low-dimensional component. Once identified, a locking mechanism engages. The training fold finalizes the parameters of the learned component, terminating the search phase. During handoff, this locked component crosses the firewall into the held-out validation fold, where it constructs the held-out adaptive moment vector. Conditional on the training information, the learned component is now mathematically treated as external to the validation observations. By enforcing this strict architectural boundary, CFAE reduces complex post-selection inference into a strictly valid, low-dimensional GMM problem. With the mechanical workflow established, we can trace the formal limit theory governing the validation fold. This highlights Theorem 1. Conditional on training data, the expectation of the externally evaluated held-out moment evaluates exactly to 0. This reduction bypasses the need for uniform limit theorems over massive dictionaries. The validation moment is fixed-dimensional. This relies on the conditional Lyapunov condition, ensuring that the local limits behave uniformly across the cross-fitted folds. It also requires feasible nuisance transfer, outlined in Assumption 3, which confirms that errors generated from training estimated nuisances shrink fast enough to be asymptotically negligible. These steps yield a valid, feasible sandwich variance formula for the adaptive estimator. Once the selection channel is isolated, the adaptive estimator safely inherits the standard first-order distribution of a classical GMM model. External validation guarantees the correct distribution theory, but it does not manufacture structural validity. We must explicitly account for the target the algorithm is chasing. This comparison shows information learning on the left, compressing already valid moments to maximize efficiency. On the right is violation learning, where algorithms search for residual directions in which the maintained model appears to fail. Adopting a failure-learned repair feature alters the underlying population target. You are no longer estimating the original parameter. The parameter being estimated on the validation fold becomes a local pseudo-true value. To treat a repaired model as a valid structural estimate, the researcher must prove explicit target preservation conditions. Researchers must account for whether their algorithmic search is optimizing existing information or diagnosing a model violation. The framework accommodates both, provided the distinction is recorded. To observe the danger of adaptive relevance in applied microeconomics, we apply these rules to David Card's landmark 1995 study on the returns to schooling. Card utilized data from the National Longitudinal Survey of Young Men in the 1970s, establishing a foundational demographic dataset to examine the causal link between education and hourly wages. This table recreates the accepted linear two-stage least squares benchmark metrics from the original study. The model yields a first-stage F statistic of 12.62 and a coefficient of 0.1324. The study achieved this by using geographic proximity to a four-year college as an instrumental variable, arguing that growing up near a college impacts education levels, but not the direct wage outcome. Now we introduce the adaptive scenario. We allow an algorithm to search a large dictionary of proximity interactions to find the mathematically strongest instrumental direction, and we evaluate it on the exact same search sample. The result is a massive same-sample first-stage F statistic of nearly 120, alongside tightly compressed standard errors. This is a mirage. Same-sample adaptive searching manufactures statistical certainty out of pure, overfitted noise. We then run the exact same dictionary of proximity interactions through the cross-fitted adaptive estimation protocol. This table now displays the corrected architecture. The proximity direction is learned strictly out of fold on the training data, and then evaluated externally on the validation observations. Evaluated cleanly, the out-of-fold F statistic collapses from 120 back to 12.22. We also observe a wide weak identification robust score set. This exposes the true, mathematically accurate range of uncertainty that the same sample selection completely hid. Instead of manufacturing tighter coefficients from weak data, the framework provides a rigorous, honest accounting of what the evidence actually supports. By decoupling discovery from inference, researchers can safely leverage algorithmic search without compromising the mathematical integrity of their results.